Good day everyone, my name is Nitin Raja, my matrix number is CE190043 and I would like to present about the system design that we simulate using MATLAB for small scale model application. We have selected hairdryer as our application, so let's jump straight into the simulation. So this is the constant value of speed which is fed into the comparator. The constant value of speed is changeable using the rotary switch. For the rotary switch, we have connected to the constant speed block so that the speed value is changeable. As you can see here, so we have connected this switch to the RPM block, which is the constant speed value block. So we have set three speed values because hairdryer usually have speed control mechanism in order to blow more air. So we have set 0 RPM for off speed. So we have set 500 RPM for low speed, 1000 RPM for medium speed and 1500 RPM for high speed. So this is how we connected to the constant block. So as you can see, when we change the state from off to low speed, the value in the constant speed block changes from 0 to 500. So as you can see, from low to medium it changes from 500 to 1000 and 1500 from medium to high. So the speed value is fed into the comparator. The function of the comparator is to check whether an input has reached the predetermined value, which in our case is speed, and the output of the comparator is fed into the PID controller. So let me show you the block parameter of the comparator. The list of the sign is sum and subtract. So let's we talk about PID controller. A PID controller is an instrument used in industrial control applications to regulate temperature, flow, pressure, speed and other process variables. PID controllers use a control loop feedback mechanism to control process variables and are the most accurate and stable converter. The working principle behind a PID controller is that the proportional, integral and derivative terms must be individually adjusted or tuned. So we talk the tuning part later. So based on the difference between these values, a correction factor is calculated and applied to the input. So let's we look into the PID controllers block parameters. Okay, so these are the default parameters that is provided by the software. So we just imported the block from the library and we have fed the comparator output into the PID controllers input. So these are the values. So this is the tuning part. So this tuning part I will explain later. Okay, let's talk about the control voltage source. The output of the PID controller is fed into the control voltage source and the output of the control voltage source is fed into the armature of the DC machine. So let's we look into the parameter of the control voltage source. So as you can see, the amplitude, phase and frequency are all in 0 because the input is controlled by the PID controller and the output is connected to the armature. So the source type that we have set for this control voltage source is AC. So you might ask why the source type is not set in DC. Okay, let me give you a simple explanation. Armature is a component of electric machine which carries alternating current. The armature winding conducts AC even on DC machines due to the commutator actions as in brushless DC motors. So that's why we have set the source type into AC. So let's we look into the DC machines. Okay, as you know, this is the DC machine. So let's we look into the parameter of the DC machine. So this is the configuration settings that I have inputted for the DC machine. So we have preset the model to 5 horsepower 240 volt 1750 rpm with a field voltage of 300 volt. So this is the preset model of the DC machine, and this is the parameter which is default by the system. Okay, the field voltage is we have set into 240 as the input for the hair dryer is 240 also. Okay, so the torque we have set into a constant value of 10. So for the torque calculation, we actually have a formula that we can use to determine the maximum value for the torque. Okay, as you know, we have a formula for the torque. So the formula is torque is equals to 5252 times horsepower over rpm. So let's we look into the DC machine's parameter again. So let's we take the values that we required, which is 5 horsepower, 1750 rpm. Okay, so these are the values that we need for in order to find the maximum torque. Okay, so we close that, and let me open calculator for you guys in order to settle this calculation. Okay, the formula is torque is equals to 5252 times horsepower over rpm. So let's calculate horsepower over rpm. So the horsepower is 5. So the rpm which is in the DC machine is 1750. So the value that we get is 0.002 something. Okay, let's we times this by 5252. So this is the maximum torque that we obtained from this calculation. So the maximum torque for this DC machine is 15. Okay, for the sake of simplicity, I just use 10 as the torque value, and the output is fed into the bus selector. So let's we talk about the bus selector. Okay, let's we look into the bus selector parameter. So these are the elements in the bus right now. So we have used all the elements as an output, so which are speed, armature current, electrical torque, and field current. So these are the elements that we have selected over here, and we have given it to the scope as an output, so we can check on its values in the display and the graph in the scope. Okay, for the speed we have set gain in the output of the bus selector for speed. So let's we look into the parameter of the gain. So the gain that we have used is 30 over pi. Okay, so the output of the gain is connected to the negative of the comparator, and the speed and the gain is connected to the multiplexer. Okay, a multiplexer or mux, its function is to combine two signals that it receives and combine it into one output, and the output is connected to a scope and a display from the mux. So mux is a multiplexer, so please take note. So that is the overall system that we have simulated using MATLAB. So let me simulate this system for you, and let me show you the result. Okay, we run the simulation. So as you can see, so these are the PID parameters, so please take note. Okay, let me run the simulation. Okay, so the simulation run is complete. So these are the output that we get. So the output for the armature current is 13.62 ampere. So B is a electrical torque. So the electrical torque that we get is 11.02. C is a field current. Field current is obtained from this DC voltage source, which is constant for all the simulation that we will do after this. So these are the output. So let me show you the graph for the output. So this is the speed versus time graph. So as you can see, we have so we, in order to achieve a steady state speed, so it will take more than 2 seconds. So let me zoom out the graph for you, or let me simulate it again using a bigger time frame. Okay, so let me run this simulation again. We have obtained this is the graph. So in order to achieve a steady state, so it will took around 5 seconds in order to achieve the smooth speed output. So the time period to achieve the speed in steady state is very big. 5 seconds, you can see 5 seconds as a small matter, but it's actually a bigger time frame. So why this is happening? Because the PID controller, the value we have set for the PID controller is random, so we didn't set it in precise. So that's why our graph will take time to achieve a steady speed. Okay, so I say before that I will explain about PID tuning. Okay, let me explain about it. Okay, as you can see, this is the parameters that we use for the PID. Before that, let me show the graphs. This is the armature current graph. Armature current versus time, we have a distortion. So it's under 1 second. Okay, this is electrical torque. So this is also same. Okay, so this is field current. Field current is always constant because we are using a DC voltage source. So this is the output of the speed. Okay, so let me do the PID tuning. Okay, as you can see, we can auto tune the PID values in this software. Okay, this is the block parameter. As you can see, this shows automated tuning. So we select tuning method based on transfer function based. So we are using a PID tuner app which is inbuilt in this system. Okay, let's press tune. Okay, so it will take some time, so let's wait for a while. Okay, so let me explain this for you. Okay, as you can see, these are the graphs that we obtain. This dotted line is the block response. This is the value that we have entered in the block parameters. So the simulation uses that value and we obtain this dotted line output. So this is the result. So for the not for the straight graph line, so that is the tuned response. Okay, let me show you the parameters. Okay, so these are the tuned parameters for PID. Okay, as you can see from the parameter that we have set before, we have set P, Kp into 1, I into 1, D we have set into 0 and we have set into 100. For the tuned response, the software produces us 0.16426 for P, I it produces 3.56, for D it produces 0.001. So we have set into 0, but it shows here 0.001. So although it's a very small number, but it gives a major difference in our results. Okay, so these are the performance and robustness using a block parameter and a tuned parameter. Okay, so these are the rise time for the tuned response, and this is for the block response. So as you can see, the time taken, so it took more than 1 second. For tuned response, it took 0.202 seconds, which is very small, within 1 second. So the overshoot that tuned response produce is very low. As you can see, the block response overshoot is very high, the peak is very low. So as you can see, so the gain margin, it's nothing. Okay, so the phase margin is 69 degree, so it's around 27.3 radian per second. So as you can see, for the block response is it shows 45.1 degree or 102 rad per second. So these are the controller parameters and the performance and robustness using a tuned response and a block response. Okay, so let me update this tuned response into our block. Okay, let me click this. This is the update block. So this is the button we need to click. So let me do that again. Okay, so after we have set the values, so these are the response which is as same as the tuned response that we are getting. Okay, so how you know that this updating have updated the values into the block? So we open back the block parameter again. So as you can see, the values are all updated in the PID controller parameters. Okay, so let me simulate again. So as you know, we have set the speed into high. Okay, so we have obtained 1500 also. Okay, let me show you the graph. As you can see, this is the response that we are getting. Though the speed, the duration that it take into getting into stable speed is very low, below than 1 second. So these are the response that we getting for adjusting the PID controller. So this is for speed, this is for fill, this is constant for electrical torque. So as you can see, we have get into 10.98. So it shows a small spike within 1 second. So for armature current also same, so it shows a little spike, then it became stable before 1 second. So these are the output that we obtain. So let me give you from the lowest to the highest. So let me run the simulation again. Okay, as you know, as you can see, so these are the values that we get. Let me check the result. Okay, so we are getting a perfect speed, steady state speed. We are getting a perfect steady state speed. Okay, so this is the simulation that we have do for this project. So that's all from me now. So I'll pass this presentation to my friend. Okay, thank you.